In this video, we're going to talk about the escape velocity when dealing with gravitational type problems with Newton's universal law of gravitation. So here's a scenario. Here's some unknown planet, M, of radius r, right there. Okay, radius r. And we have a spaceship on the surface of the planet, and we want to have it completely escape the planet's gravitational pull. So as we blast off with a certain velocity, we'll travel along here in a straight line, go along here. And as I do that, the gravitational potential energy will be lower and lower because the force of gravity is lower and lower. So I keep going way out here, I will slow down because I'm working against the pull of the planet. And if I get to a place out here, where there's no more force goes to zero, or potential energy goes to zero, out here at r is equal to infinity. So if I get to infinity, there's a point out here where if I just make it, okay, if I have some minimum amount of kinetic energy, let's say, I get to all the way over here, then I'll reach this point where if there's no potential, and I've used up all my kinetic energy, then I'll get to this point and I will not fall back to the Earth because I have no more potential, no more gravitational potential. Okay, if I get to this point at infinity. If I were a point closer, not quite at infinity, I'd still have a little potential, and then I would slowly fall back to the Earth if I exhausted all my kinetic energy. So basically, I'm going to get to infinity. And if you think about a race, if you start off with a race, you have some kinetic energy, and you're racing, and you're like a mile race. You keep going, you have some kinetic energy. You get tired, your potential decreases, you slow down, and then you just make it to the finish line here. You can think of that as like a race. You're trying to get to that point. So from an energy point of view, we have the energy at point A, and we have the energy at point B over here. And got my buckets here, so those energies are equal. Energy at point A, energy at point B. And here's my kinetic energy bucket here at point A. Here's my gravitational. It's upside down for our negative potential energies. And we have kinetic over here at point B. And my gravitational bucket over here at point B. UGA, KA. So I'm on the planet and I do have kinetic energy because I have some rockets that are going to boost me. I have some kinetic energy. I'm not at infinity, so I do have some gravitational potential. Now, the minimum amount of kinetic energy means I get there, I travel, and I slow down. So my kinetic energy, actually, for the minimum, it's going to be zero. I'm not going to have anything left. If I had more than the minimum, then I can go further. But if I have the minimum blasting off, I will exhaust all of it. No more kinetic. And at infinity, I have no potential. So this looks like 1/2 mva squared minus g m over r equals a grand total of 0. So from a numerical point of view, this might be, let's say, 5 joules here minus 5 joules there equals 0. And the larger the mass of the planet, these quantities are, masses are, for instance, this is Jupiter, Saturn, the more potential you're going to have. This might be minus 15. That would require me to have 15 joules of kinetic energy, so a higher velocity. Whereas a smaller planet, like Mercury or the dwarf planet Pluto, has a very small mass comparatively. This might be 1 joule, so I would only need 1 joule of kinetic energy, a lot less energy. So the gravitational pull of the planet itself comes into play as well. So that's an analysis of how to find the minimum amount of kinetic energy, or the escape velocity of an object when it wants to leave a planet.